Welcome to this next installment in the series The Ray Tracer Challenge by James Buck, where I implement in a language which is new to me, Rust, a ray tracer based on the book by James Buck, which chapter for chapter guides us through the implementation. Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun. First of all, you may notice something new if you have watched me before. Now I am in the bottom right corner down there with a kind of a virtual green screen behind me, cutting out all this background behind me, which doesn't need to be there especially. So let's see how this works out. I'm not 100% sure I will do this in the next episode as well. I'm not 100% sure I might not even install a real green screen behind me, but currently let's just try it out and see how this works, because I really like the idea of having more screen estate here for you to see and not wasted by the background of my office here. So I guess we could try this. And this virtual background screen was a quite easy way to create, and yeah, so let's see if this works out for us. Okay, so I guess we will jump into the code then, because I have to show you something I did in the meantime, which I did not record actually. It's not that kind of a problem here, because it is something which is essentially not in the book, but it is something I wanted to do and just wanted to play around with. So what did I do? I implemented PNG output support so that we can now render PNG images and not only PPM images. Just due to the fact that I have been made aware that it is quite hard for non-macOS operating systems to open those PPM files just like doing it in the image viewer. I can just click them and they open. That's mostly not possible with other operating systems. So I thought it might be quite a good way to implement PNG, which can be opened by nearly everything. So yeah, I did that. And in order to do that, I just refactored some things first. I refactored the canvas for once, essentially by implementing traits and using this arbitrary float type, as we already did in the last session bonus video, refactoring the matrices to use floats instead of hard-coded F64s. So I've just done this to color as well, and to, canvas as well. And another thing you will notice here is that for once, canvas is now a lot smaller. It's just those lines here, and all the PPM stuff has been moved to a different file, which you can see here on the left. So there is a different file now for each of the output methods. We will take a look at this soon. Furthermore, I've implemented a sized trait for canvas and defined it above here, and it's simply something that allows us to easily get width and height defined of this structure. So now let's take a look at the PPM implementation. Most of it you know before, but the structure has a little bit been changed. So we still have our create PPM header function as before, and the toPPM trait now has the enforcement to implement this toPPM function, which then, as before, simply returns a vector of bytes. The 2ppm implementation has been changed a little bit by me because now it is based on 2RGB32, which we'll see in a second. And it is essentially an implementation not specifically for Canvas, but for everything that implements the 2RGB32 trait and the sized trait. So Canvas will match because we will see in a second that Canvas implements 2RGB-A32 now, but it is actually possible to use it with everything that implements those two traits. And I've changed something else as well. I've switched from the iteration style to or the for loop style to an iterator usage style using closures like this one here. Closures are more or less functions in Rust which can bind and capture free variables which are in the outer scope. So inside this closure function, we have access, for example, to those two variables here. This isn't the neatest way to do it, but is at least the one which I found which seems to be quite effective, because all those evaluation functions we will check and discuss in a second are evaluated lazy. So only when the last one of those functions essentially needs something, the structures before are evaluated and passed through this chain in order to give us the data we need. And this is quite nice. So before we are going further into this, let's actually check what this 2RGBA32 provides us with, because it is essentially the first call we are doing here on the implementing structure. So 2RGBA32 does nothing more than just providing us with a byte representation, an 8-bit per pixel with alpha channel representation of our color data. So essentially we are getting back a vector with bytes as well, or as you can see here in the method declaration. And essentially we are just we are clamping our color values between 0 and 1, and then taking the value, converting it to a value between 0 and 255, mapping all those things and pushing just out a byte stream of RGBA, 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 and so on and so on. So essentially we are just outputting a coherent byte stream of RGBA data, where in our case of the canvas, as we don't have any alpha opacity there, especially for everything, we will during the renderings, but we won't have it in the output because our color model cannot represent that at the moment. Maybe this will change later on, I have no idea, but at the moment it's just always fully opaque so that we can always see what we are doing there. Yeah, and that is essentially the RGBA trait, and what our implementation, where is it, ppm now does is, it just converts this into an iterator, and then it maps those into actually the byte. So what it does is it makes essentially using format a string out of everything. That is a function we had before, which created a lot of different strings we needed to do some of the conversion work. So essentially this one will give us the number representation of the byte, which is quite nice. So after that we do an enumeration which adds an index to each of those values, and then we simply throw away each fourth value. We throw away the alpha channel because we don't need alpha channel for our output in ppm. After that we do an enumeration again because we need now new clean enumerated values, because otherwise every fourth one would not be there, and we need the enumerated value actually to calculate the current image row based on this. And then we start our conversion process by doing it the same way as we did before. We calculate the current row. If the current row is a next one, we simply inject a new line here, and so on and so on. All this code has been simply copied over from the old implementation. And once we are finished with that, we just return each of those data blobs, or data blocks, better said. And the flat map here will automatically create one coherent byte stream of all of that, which is quite nice. Once we are done with that, we are creating a ppm header, creating an iterator from that, chaining the pixel data we have just generated into this. We could have inlined this here, but no reason to do it actually. And then we are chaining a new line at the end, which is the new line at the end of the file. And then we are doing a collect, which actually converts the iterator back into a vector which we then can return. So we are just collect essentially only goes then, as I said, all this is lazy evaluated, then goes ahead and iterates through all of the data set and generates a new one which it can then return. We may even change this in the future to not collect it at this point, but to stream it further on for us to process, but we will see. Maybe we will even implement a writer trait there, which we can then pipe directly into a file, but yeah. So we have converted this to ppm, so let's take a look at 2png. 2png more or less is very simple because I've used an existing crate there. I have installed this PNG crate, and this PNG crate allows us to encode a PNG quite easily actually, as you can see. So what we are then doing is we are simply doing exactly the same. We are defining the trait here, which allows us to do a 2PNG. It gives us a byte stream back as well. And then we are implementing 2PNG again for everything that is 2RGBA32 and that is sized, because we need those two information. We need once the bits, the byte stream, the data stream of colors, and we need the size of the image, and that is everything that we need to actually generate a PNG for our image. So we are then implementing this here by first creating a new vector of data which holds our new image data. We are then instantiating from this crate a new PNG encoder using the width and the height we have from our sized trait. We are then setting the color depth of the result image we want to generate to RGBA. The color space mode. So we want RGBA. We set the color depth to 8 bits. 8 bits per color. So 32 bits for each of the tuples which represent RGBA. Then we create something which is called a writer, which we get by using write header, which is then written out. And then we tell the writer to write the image data by giving it a reference to the vector, which essentially is our RGBA data. So we are just writing this out. Then we are doing something here. We are after that just telling Rust to kind of throw away the ownership of this writer, because we want essentially to be allowed to take this vector back here, because we now know that nothing can actually have it assigned, or that we are able to access it back, because the PNG encoder here needs something during construction which implements the write trait. The write trait is implemented by vector, which is nice. The write trait is usually something that is implemented on all of the IO streams in Rust, which allows us to write to files or read from files and stuff like that. Write obviously allows us only to write, but there is, for example, something like seek, which allows us to move around in there and stuff like that we need for reading as well. So what we are doing here is we are using the vector, and a mutable vector reference actually implements write. And giving this to the encoder, because we don't want to write directly to a file, but we want to write to memory, because our trait is defined as returning just a memory reference to our data bytes. So we are using this. But if we wouldn't drop the writer here, we would have essentially a problem with this, as it is not allowing us to access the V here. If I remove this, I get immediately the error message: I cannot move out of V because it is borrowed. Move out of V occurs here. So we are actually moving the ownership of this vector out of this function, but it is still borrowed by this writer. And this is essentially, of course, something we cannot do. So if I just throw away this writer here, as we know we don't need it anymore, there are no more bytes or data to be written with it, I can actually move the vector out now because it isn't borrowed anymore. The writer doesn't have a borrow to this reference here anymore, so there is no problem. Because there doesn't exist a writer anymore. Yeah, and once we did that, I could easily just implement this writing PNG function by just creating a PNG here and then writing it out to the disk. And if I'm now executing cargo run bin chapter 2, you can see that it is first outputting the ppm and then the PNG. And if I open this one up here, I now have a PNG image which has our graphic inside, which is really nice. And in the future, we can now render out PNGs with our rendered and ray traced scenes as well. So that is actually what I did. And I did this until now in a different branch. And what I'm going to do now is I'm checking out our main branch. And then I am going to git merge png output. And let's not push, but push. Let's push this. So now we have PNG output within our main branch. There we are. Yeah, this was a quite quick run through. Not so quick when I'm looking at the time, but I wanted to explain this to you, as it are some quite potential changes there, which might otherwise irritate you if you are taking a look at the code, if you don't know where this comes from. And as I said in the first episode, I want to develop this with you in unison, so we want to do it together. So I want to explain stuff I do. Yeah. So now that we have this, we can actually go on and implement the next chapter, which is chapter 4 actually. And I'm just seeing maybe I should move a little bit more to here. Looks kind of weird, I guess, if I'm so completely out of the picture, if my arm is somewhere here. Okay, so let's get going and implement chapter 4 now, or start implementing chapter 4. In the last session, we actually the one before the bonus session where I did all the refactoring, actually we implemented matrix operations and all kinds of matrix stuff, like matrix multiplication and stuff like that. And now we are going to use this to implement the usual transformation operations we later on need within our ray tracer. Something like to move objects around, or to rotate them, or to kind of perspectively trying to squish them, or to scale them, or something like that. All of those operations are needed later on, because it is not so easy doable to describe mathematically a whole scene consisting of a lot of different objects. It is a lot easier to describe each of the objects as if they were in the center exactly of our coordinate system, and then just transform those to the points where we need them in the world. So that makes things a lot easier, because when we are later on calculating ray intersections and ray object intersections and stuff like that, it is a lot easier to do this if we always can assume we have this consistent model of just of just having everything in the center of our universe, so to speak. And so we can actually implement this for one sphere model and then use it at 200 different places within the scene, which is kind of nice, actually. So, and we are using matrices for this. There are different matrices for a lot of different operations, like, for example, a translation matrix, a rotation matrix, a skewing matrix, a scaling matrix, and stuff like that. So we can create different kinds of matrices to accomplish all of those more or less needed transform operations. And so that we don't need to always write those quite complex, sometimes quite complex matrices, we just want to do something like give me a rotation matrix which rotates around this axis by amount x. And this is essentially what we are doing now in this chapter. We are implementing this. And I have done one thing. I have gone ahead and implemented the tests before this session. So I have not implemented the solution in any kind, but I have written the tests because I realized, and I will test this. So you see not only my picture in the right corner on the bottom is new, but the thing we are trying to do here will change a little bit as well, because or better said, how we are doing it, because I realized that having me just kind of transfer the test data from the book into the project is taking up a lot of time, and it is essentially hindering us in getting along with the implementation, and it's quite it's slow, and it's not that great. So I thought maybe it would be a better idea to simply try and have us or have me do this beforehand, and then just take the tests, talk with you about them, what they are doing, so that I don't have to write out all the values there, and then we can start implementing. And let's just see and try and see how this works. So I've actually a ray tracer challenge prepared here, which is, as you can see, the same Git repository but in another branch, the chapter 4 preparation branch. And if I'm now opening source matrix there, I trust this. I have written it myself. I should actually trust this. So there you can see that this matrix implementation has a certain amount of tests there which weren't there before. So there is something about translation matrices. Yes. So this was the last one we have written before, which was multiplying a product by its inverse. So simply we implemented all of this matrix inversion stuff. And what we are now going to do, we are putting this to use. The first thing we are going to do is implement translation. And something I need to clarify here, as we are going to talk about this, or you might ask yourself, and the book talked about it as well. Let me open our matrix implementation here so I can copy over the stuff here just when we are doing it. So is actually that why not, or translation applied to a vector is not different from just adding two vectors together. So we could add one vector to another vector, and we have actually moved it by this. It's how vector addition works. So why do we need a matrix for this? And the book talks about this as well, but it is quite clear if you think of it, if you know what you can do with matrices. First of all, we want to use matrices for all our transformations so that we are doing it in a unique way. And therefore we are using translation matrices as well. Furthermore, and that is even more important, we can multiply multiple transformation matrices together to create one final transformation matrix, which does all the different transformations after each other. So we can kind of pre-calculate a transformation operation, including different kinds of translation, rotation, scaling, shearing, and even with different steps in between. So you might think of if you translate something, then rotate around the origin point of the coordinate system, and then translate it again, and then rotate it again. It will move it slightly or completely different than it would if you would do this in one go. So we can then create this final transformation matrix, which we can store there for example, for this object or this world configuration, and apply to this object over and over again. And we don't need to apply all these different operations all the time, which speeds up things a lot, and it makes actually reasoning about this a lot easier. So we are actually implementing translation as well as part of a matrix multiplication. So the first test here is now multiplying by a translation matrix. So what we have here is we have something that might work or might not. Let's get this test here to see that it of course does not work yet, because we haven't implemented it yet. So we should quickly see, this is the first test, which simply tells our matrix it wants a translation by the x of 5, y of -3, and z of 2. And then we have a point here, and we want the expected result point, of course, to be translated by these values. So the -3 plus 5 gets 2, the 4 minus 3 gets 1, the 5 plus 2 gets 7. So yeah, we are actually assuming just that when we are multiplying the transformation matrix with our point, we are actually getting back the new translated point. And yeah, as you have guessed, there is no translation implementation yet, so this is completely right in the test. It says there is no translation. So let's implement the translation implementation. Where do we need to go for this? Where is it? Where is it? There. I have to take a look if we can actually split up tests from the implementation, even though I like that they are directly in combination with each other. I would like it more if they had were in the same folder with a slightly different file name, so that we can actually switch, but we will see. So let's take a look here. What do we want to do here? We want to implement the translation function, but where do we need to implement it? What is this here? It seems to me that this is all the implementation stuff for a matrix T4. And actually we can only create a matrix T4. I guess we can only create a translation matrix. Yeah, we can only create or reasonably we can only create a translation matrix, a 4x4 matrix, because everything else doesn't make a lot of sense in our three-dimensional coordinate system. So let's just implement it here and say we have now pub translation, and we want to take it x with this, which is t, I guess, and y, which is t, and z, which is t, and it returns a matrix of t with 4 by 4 elements. And now let's just create this matrix. So let's just do a from, and let's simply put our matrix in here. So what we are doing here is we need an identity matrix. So let's create an identity matrix, and you will see where I'm going with this. So we have this one, then we need to move the one diagonal, the one to the right, to have this diagonals of ones. So So now we are doing this here and moving this one here, and then we are doing this there and moving this one there. So now that we have done this, we have the identity matrix, which is not missing fn. Oh, I'm missing an fn. That's completely true. So unused, yeah, and it now tells us we haven't actually used our translation stuff here. So why didn't we? Because we have not yet put it in there. So essentially, if we would use this one, it's a as you can see, it's a there is a 1, there is a 1, there is a 1 in the diagonal. It's an identity matrix. So if we multiply this with a vector, simply with a point, simply the result does it's the same result. It's the identity. What we want now to do is we want to translate it by the given x, y, and z coordinates, and we are doing this by simply putting it here in the last column, just in row 0, 1, and 2. And with this, actually, we can check by our test that this is actually working. Let me put this into the space there. Oh, I need to go back to the Ray Tracer Challenge, our real folder here. And if I do now cargo test, it should actually, yeah, all the tests are now running. So there should be some matrix test. Let's just do a test. What is it? Translation. Just run this. Run this one test here. And yeah, unit tests, one passed. Where is it? There, matrix, multiplying by translation matrix, and it actually works. So if you are taking a look at how matrix multiplication works, you can easily figure out that by just putting the values here in the last column of a 4x4 matrix, and this is essentially, I said that in the beginning that we need 4x4 matrices and not 3x3 matrices, as you might think if you are thinking about three-dimensional space and that you only need 3 dimensions. You can't actually then create a matrix which does translation. So then you would need a separate vector. And if you put this vector into the translation, into the matrix, you get a 4x4 matrix, and you are essentially capable of working with this properly. So it's actually quite nice. You can incorporate translation into your matrix, and it just works like that. So now we have something that creates us a translation matrix, which is quite nice. So let's see what the next test would be. And now I think I'm going to just do something like I'm going to move split right. So maybe just let's put the tests here. With me not here in the above corner, we can actually now do this. And let's make this a little bit bigger. And now let's put the implementation to the left, and so we can work a lot more easy. This is actually the way I would usually do this. So let's move over this prepared tests here. And yeah, so that's nice. So the next test is we are ensuring that the multiplication with the inversion of a translation matrix actually moves something into the opposite direction, which is actually an effect of doing it by matrix as well. We can invert it, and then it moves into the opposite direction. So we can see here that we have a translation matrix again of 5, -3, 2. We have the same point here, -3, 4, and 5. And now if we are applying the transform inverse to this point, we are actually expecting that it is moving in the opposite direction. It is not moving 5 in the x direction, but it is moving in the opposite direction 5, so -5. So it should move from -3 to -8, from 4 to 7 by adding those 3 here. and from 2 to 3 by wait a second. I guess I've missed a minus here. I would assume this should be -3. Let's check. Let's just check. Okay, what what is going on there? Why is this not? Let me think about this. We have the translation of 2. It should... Oh, no. I was thinking the wrong way. I thought this was the point, but this is the translation. Actually, we have the point 5, and we are moving 2 from it, so we are moving into the opposite direction, so -2, so we are moving to 3. Okay, this works. But as you have just seen, our implementation already passes that, because that is how matrix implementations or matrices work. You can invert them, and you have seen the last time how we can calculate that. And if you can invert them, you can actually produce this result without really thinking about it. The inverse of the given matrix will do the of the translation matrix will do the exact opposite of the operation. Nice. So what do we have next? Next we have something which is kind of interesting. Let's copy this. The thing with vectors. So what happens if we would translate a vector? Essentially, a vector just tells us a direction and kind of force or length into space. It doesn't actually give us a point in space. That's what a point is for. And so if we actually translate a vector, it should not move at all. So let's test this. Let's just make this point we had here to a vector now, and let's multiply this there, and let's just expect that the expected result is the same as before. So it should not move. And let's check this. And yeah, this works. But the question is, why does it work? So do you remember that the vector was implemented as well as a 4-dimensional vector with a W component of 0? And we especially decided to implement points with a first component which was 1, and the vector with the fourth component which was 0. So what actually happens here now is, if you multiply this matrix with a vector, if you take a look back at how matrix multiplications work out, you will see that if actually the fourth row of the vector being 0 cancels out this whole column of the matrix in the multiplication. So essentially there will only be the result with regards to the identity matrix which we have left here. And so there is no translation, and this is exactly what we want for vectors. We do not want to translate them. Nice. Yeah, so I guess we have just implemented git add source matrix, git ci, implemented. Let's call this translation transform. Nice. This was easy. So let's take a look at the next one. The next one actually is scaling. So yeah, let's do scaling, I guess. So let's paste this test here, which is a scaling matrix applied to a point. And now you can see we don't have scaling matrices or a scaling matrix there as well. So now let's see. Scaling. Scaling would be to make a value bigger. Yeah, to kind of Scale points. So if we have an object which is consistent of a lot of different vertices, like a sphere, for example, or other stuff, which is a mathematical construct, we want to make it bigger. So we want to make and maybe want to be able to scale points. So what we are doing here now is we are calling this scaling here, which should actually scale all of the given points by their appropriate value here. So this should be 2 times -4, which is then -8. This should be 3 times 6, which is 18. And this should be 4 times 8, which is 32. So yeah, sounds reasonable, but how do we implement this? Actually, it's more or less the same thing. Let's take this base matrix here, or base thingy here, so we don't need to write everything again. So let's call this scaling. And now scaling looks a little bit different. Let me first make an identity matrix back out of this. So by just doing this, now we have an identity matrix, a clean slate kind of to start with again. And now if you think of it, what does the identity matrix do? The identity matrix uses this diagonal here with regards to matrix multiplication to actually have everything be the same as before. So essentially ensuring that we multiply each of the components one time with 1 to get the same result, and the rest of the time multiply everything else with 0 to just cancel it out, so that we have the same result in the multiplication as before. And if you are thinking about this way, you can easily deduce that this should be our scaling matrix. By just adapting this this diagonal, at least the 3 initial parts of the diagonal, to x, y, and z, we are multiplying the components with this value and just leaving everything else as it was before. So I'm just trying to remember now my my format shortcut here. So whoops. That was definitely the wrong one. I didn't want to press this one. So yeah, formatted. So let's, I guess let's run tests then. And let's test, what did we do? Scale, didn't we? Did we call it scaling? Let's just run it like this. And we can see that, yeah, a scaling matrix. So let's maybe do scaling there. Let's maybe do scaling. And we see that this unit test, a scaling matrix, does the correct calculation, which is really nice. So my keyboard shortcuts don't work like I would have them to today. But yeah, so we have actually implemented scaling. So is there a next test we are needed to implement for scaling? A scaling matrix is applied to a vector. Now, if we are scaling a vector, we actually want to be able to scale a vector, because a vector, as I said, shows us a direction somewhere into the space, but, and this is important, it does not only show us a direction into space, it shows us a kind of a force into space, a length. A length is assigned to this vector. And by scaling a vector up, we are essentially keeping the direction, but scaling this length of the vector. And we want to do that. We need to do that. So we have a test here, which essentially makes sure that exactly the same scaling is applied to a vector here than it is to exactly the same scaling here is applied to a vector than it is to a point, as you can see here above. The values are exactly the same, but the data structure is another one, which now has in the W component a 0 and not a 1. And if we are running the test now, that was the wrong shortcut there. It should actually let's see. Yeah, applied to a vector, it runs as well. So the scaling matrix works as well for vectors, as it should. So what's now if we apply the inverse of a scaling? So let's check that as well. Essentially the same thing here than before. We are just... I did something wrong with this? Yeah, I did. I should have multiplied it with inverse transform here. As you can see, I've just transform. As you can see by stuff like this, I really did not use this code before. I really just wrote those tests without even executing them once. So just to speed up things a little bit. But now, what do we need to do here? We want to multiply by the inverse of a scaling matrix. And what should it actually do? It should scale into the reverse direction. It should actually reverse the scaling. So a scaling by 2 should actually do a scaling by 0.5. So it should make this thing half as big, and so on. So this is exactly what we are testing here. We have a scaling matrix, the same as before. We have a vector here, and we are essentially checking that this vector is now, if this is applied against this, as you can see, we have 2, 3, 4, and 4, 6, 8. Here divided by 2, divided by 3, divided by 4, and we actually get the negative result here, 2, 2, and 2. And this is what we would expect. So let's check if this is actually what is happening there. And as you can see, a scaling matrix multiplying by the inverse is doing right as well. So yeah, this is nice. So what is the next one? What is actually, yeah, that's kind of that's the last one from the scaling thingies. And it's quite nice to have this one as well. It is the explanation actually of reflection. So if we want to reflect something with regards to a certain axis, so in this case we are actually want to reflect something to the x-axis. So if it was here, it will be, if this is the x-axis, for example, if it was here, it will be there then. So this is actually working out as if we do a negative scaling by this axis by -1, it will actually calculate us exactly this this reflection. And this is actually what we are trying to figure out here. We have a scaling matrix which has a -1 in the x component and 1 in the y and z component, to just simply do not touching those. And we have 2, 3, and 4, and we are expecting then -2, 3, and 4, which is to be expected actually, kind of, but let's make sure that this works as intended. So yeah, reflection is scaling by a negative value. So now we know how to do reflection. Which is quite nice, I guess. So yeah, we just implemented, and this is really nice, scaling as well. We have our next transformation implemented. So let's source matrix, let's add this as well, and let's do a implemented scaling transform. And now that I see that there is an output PNG, I actually added the output ppm to my gitignore file to not have this lingering around all the time. And I should do the same with the VS Code folder for now. I may commit it in the future, but I need to take a look at further information there. So let's add this one quickly. Added PNG output as well as IDE configuration to gitignore. So let's push this. So okay, we have implemented scaling. What is the next thing? The next thing is rotation. And rotation now gets a little bit more interesting, I would say. It is not a lot harder to do, but it is a little bit interesting. So let's take a look at this rotation test I've just copied in. Let's focus on rotation around one axis for now. So there are a couple of things we need to consider for this. First of all, rotation amount, how much we rotate, is always given in this calculations in radians, because we will be using sine and cosine functions, and they by default take radians as parameters. And so what is a radian? A radian is actually the amount of rotation given inside a circle construct defined by p, so that 2p, so 2 times pi, will actually be a full rotation. So 1 times pi is a half a rotation. As you can see here, full quarter, so pi divided by 2 is a quarter, and so on and so on. So we can actually easily calculate the radiant. So we can calculate the radiant value based on the degree value. So if you have something like 180 degrees, it's quite easy to calculate this. You simply multiply it by pi and divide it by 180. So if you want to calculate from degrees to radians, you simply go ahead and multiply it by pi divided by 180, and you will have your result there. But we could implement some sort of conversion for that, but we are not going this route. We should actually learn to think in this radiant calculations and radiant values anyways for everything else to come. And if you are not used to this, start thinking about this now. Just so you know, 2 times pi is a full rotation, 360 degrees. So that is essentially what we are giving the system here. And now we have a problem, because we need this pi value. And I've already figured this out, but I don't anymore know in which package it was. Yeah, I've just Googled this one, and it was in the std f64 consts pi. So let's import this one. And then we should be able to use this here. As you can see now, this one is not telling us anymore that it does not know what this value is. So it is here now. Perfect. So we can use it. But now, of course, we don't have a rotation x. Yeah, we don't have it. So let's start implementing this one, I guess. No, we wanted the tests here. And we wanted to implement over on this side. So pub fn rotation x, which should then take radians or radiant, or let's just call it r, I guess, which is then of type T, and it will return a matrix of type T and 4 in the dimension. So let's reuse this here as well again. So let's make this one, where is it? Wait a second, what happened here? Did I not? Oh, this is, yeah, it's kind of hard to read. So this will be 1 again. So, and this will be 1. And I just removed the 4th component there. So let's add this as well. This will be 1 again. And this one will be 1. I'm quite aware that I could create an identity matrix here easily because we have a function for that, and then just set the row and column index and the value directly. But I'm usually thinking that this is more easy to read because we can see where in the matrix these values are. Even though I would love to have this a little bit differently formatted, because I would really much like it to have it like, just as example, to have it like this, of course, so that I can directly see where each value is and not have this kind of weird spacing in there. But the problem is that the Rust formatter here will automatically change this again. But I could, that is something I could actually quickly do, is Rust format not format block or something like this. Maybe we can disable this for a specific area. Yeah, I guess let's do that, because I like the idea of having this properly shown and moved so that I can directly see how this matrix looks. So let's check if this is working. Yeah, now if I format, it skips this area. Nice one. So now I can do, I can put this here, and let's see. Where do we need? We need this here then, and this needs to go here. And now we can easily see that there is this diagonal which is set. And yeah, I really much like that. That is nice. That is really nice, and that is really nice. So let's just put it here for the rotation as well. So it was a good idea to Google that. So yeah, we have now this rotation, and now a rotation matrix, and this is something I always need to look up, but it's fortunately printed out in the book, is something I definitely can never remember. So as I said before, it is using sine and cosine, and actually it is using a combination of different sine and cosine values with different signages in front of them, so a minus sign of something and a plus sign of something, and combines a matrix out of it which does actually the rotation. Rotation around different axes is simply creating a matrix for this kind of rotation for this axis with all the sine and cosines in it at specific places within the matrix. So if you want a rotation around x, you will have the sine and cosine stuff at specific places, and you will have exactly the same sine and cosine values for a rotation around y, for example, but just in different places. So let's format this one here properly up, so it is square again, which it is now, I guess. Yeah. So now let's take a look. The rotation around x is done by replacing this value here with the given value r, but the cosine of it. So yeah, the next one is here replaced by minus r sine. So let's do this, and now below that is the sine of r. So we are taking the sinus of r here. No, I needed to delete this one. So, and this one then is again the cosine of r. Oh, cosine of r. And this should do it actually. So if we have this block of 4 values in here, this should actually rotate our or create a rotation matrix to rotate our points around the x-axis. And essentially this one does this in a left-hand side coordinate system. So if we are pointing our with our left hand, if we are pointing towards or in the direction of the axis we are moving, for example the x-axis here, and we are grabbing this axis in the direction of our fingers like this, then this is the rotation direction. So if x goes there, if this is plus x, then the rotation direction will be like this. So, and this should actually create this rotation, and this is what our test here checks. So let's first of all, because it is a lot easier to see here, let's take a look at this full quarter multiplied by the point thingy here. So we are rotating the x-axis here. Yeah, we are rotating the x around the x-axis by a quarter, so exactly 90 degrees. So if you think of this, if you have a point which is think of it as a direction from the center of your coordinate system. So if you have a point which is kind of here, it's just in the y. It has an x of 0 and it has a y here, and you are rotating it around this one, the x-axis. So you are actually kind of moving it like this. And if you are moving it like this 90 degrees, it will essentially end up on your z-axis into the screen and lying flat there. And this should be actually the result that we get. Let's check. Cargo test rotating. So let's check, and yes. We are actually getting a warning here. Why are we getting a warning here? Okay, yeah, I see why we're getting a warning here. We will correct that in a second. But the rotating a point around the x-axis is complete and works. So essentially this function here does what it should. So let's quickly fix this warning here. Why do we get a warning? We get a warning because we imported this one here, but our implementation essentially isn't using Pi. Only our tests are using Pi. So let's only import Pi for our tests. And now there should not be any more errors or warnings or anything. There's our run, and it doesn't have any more warnings. Nice one. So this is okay. I like that. So yeah, let's go ahead and do the next thing. We actually implemented rotation around X, and this is quite a complex thing actually. So where are the rest of our tests? Yeah, I guess after rotating in X direction, the direction to one of the sides, we are again, as always, doing it with the inverse of the rotation, because yeah, the rotation reversed, or the inverse of a rotation matrix, actually calculates the rotation into the other direction. So just rotate it 90 degrees counter. So if this is our X again, we are just rotating it kind of this way, so into the other direction. I can't do this without breaking my arm, but I guess you get the idea of that. So let's take a look at how this ends up and if this works. So yeah, and as you might have guessed, oh no, it didn't execute this, the inverse of rotation. Oh, because this is now called rotation. Okay, let's just execute all tests. So it will be in here somehow, test. Okay, let's inverse of, let's rotation, just to be sure. I just want to be sure. There it is. the inverse of an X rotation rotates in the opposite direction, and it does. And what is the result here? Yeah, the expected result here is now a little bit more complicated, as we are just doing a half quarter rotation. But we could easily, I guess, check that it is for the full quarter thingy doing its thing as well. Let's do that. Full quarter, because we can more easily understand or visualize in our heads what a 90-degree rotation, a quarter rotation actually means. So let's do this here. We now have this full quarter, and let's then call this inverse half quarter, and let's do an inverse full quarter. And there we are doing the full quarter inverse. And now we are actually, yeah, we are doing, this is of course then the inverse half quarter as before, and we can copy that, or let's copy that, because it is nearer in the vicinity of our expected result, because now of course this is rotated and flipped to the other side of Z. So it is actually in front of us and not into the screen, but before the screen. So this should actually provide us with a proper output here. Let's run this test, and as you can see, it is exactly doing what we would have expected it to do. And if I move this one up, you can even see what I've written there. So I have just asserted now that the inverse full quarter multiplied with the point P is essentially this vector, where this one is just flipped forward out of the screen. So it's exactly what we would expect there. So yeah, nice, I guess. It looks quite nice to me. So what is next on our agenda to rotation? So rotating a point around the y-axis. So yeah, I guess after we have done it for x, it shouldn't be that hard to do it for y, should it? So rotating a point around the y-axis. Yeah, so it is complaining again that it doesn't know about the rotation y function now. Makes sense as well, as we haven't implemented it. And I guess we just assume it will be mostly the same. Let's move this one up. It will be mostly the same as the rotation x. And as you might have guessed right, because it will mostly be the same. And again, those are things, just Google them or look them up in Wikipedia, or I guess in school, maybe for some sort of test, I might have remembered exactly how to do those. I might at one point, I'm quite sure at one point in my life, I understood even the concept of how you are getting to these matrices and how you can actually create them from scratch and prove that they work and do what you think they do. But now just look them up and write them down. This is essentially what we are doing here. So this is all the groundwork we are currently doing to then later on create pictures of ray traced stuff. And I can now say in the next chapter, we will actually create our first ray traced sphere. It won't look completely correct, or it will look very basic because there will not be any lighting, but we will have ray traced a sphere, and we will see this in a picture. So that will be the next chapter. Yeah, I read up ahead a few chapters, but I haven't done any work on this yet. So let's implement now rotation y. So how does rotation y work? Essentially, I have to look it up. So now we have the cosine is now. Let me just check. So I guess we just make this one an identity matrix again, just to have this a little bit more easy. And then maybe I should copy one of those identity matrices somewhere, but yeah, no, I don't think we really need that, do we? So let's just do it this way, and let's do what has to be here, a T1, I guess. And there is a 1 there, and there we need to remove this sign here and create a T0. So, and this needs to be there then again. So yeah, this is an, yeah, rotation Y, nice. And yeah, I guess now we need to take care of where all this stuff needs to be. So the first value here needs to be the cosine of R. So we are just injecting this there. The second one is a 0, and there is in the first row, third column is a sine of R. I'm actually taking quite a hard time to getting used to the way Rust's calling convention on this is. It's a kind of a reverse Polish notation, like in a calculator like that. You may know those things where you put in the two operands and then the operation, something like this. It's kind of weird, but understand why they are doing it, because all of this stuff is only traits implemented on their value data, and it's very consistent. This is something I really like in Rust until now. I think the whole language concept is really consistent, but it's kind of, I am always thinking about writing something like this, cosinus R. But of course it is like, take this value and call on the, whatever this trait is called. Maybe we can find out. Yeah, I guess it's just a basic implementation, number something on this thing. But yeah, it's so call this one, and yeah, it is consistent, but it's still a little bit weird to me. So this is a minus sign R here, which is there in the third row, first column, and then we have in the third row, third column, have a cosine of R again. So let's take a look. Looks good to me. Let's execute some tests. This is called rotating. Rotating, there we go. Oh, and it failed. We did something wrong, obviously. So rotating a point around the y-axis, panicked at asserting fuzzy equality tuple something something is equal to, so are those values really different? They look quite the same to me. 7071067 7071067. So this one looks quite the same. And what is with this one? It's like y. Oh, so we did something wrong there. Our rotation values are kind of correct, but what's wrong is this in between. So we have a y1.0 there, and we seem to have expected a 0.0. So this is what's wrong with it. So at one time I need to take a look at, maybe I will do this off the recording, if there is a better way of outputting this. Like I know it from different other languages which create a diff then and stuff like that for you to color highlight it, read it better. So I guess we have somewhere in here we have some one which shouldn't be there is a one which shouldn't be there. There should be a, oh, there should be a 0. I think we did not catch that when we created back our original identity matrix. So yeah, now it's running. Nice. So is there another test? I guess there will be an inverse test. No. Okay, we have just checked the inverse with the rotation of the x. Yeah, I guess this is okay. I guess we don't especially need another one for each of the x's. Because I guess the test more or less was there to show us in the book the concept of this inversion of rotation, which is really nice, so that we can do this. But the test essentially is not needed, as we have already tests that check that our inversion of matrices calculation is correct. So yeah. So let's implement, I guess, around rotating around z then. So let's copy this again. And oh, I again did not scroll up. So this is our rotation around z here. So let's rotate around that z, and around z is now actually having all those values in the upper left corner, kind of. So we have a cosine of r here, followed by a minus r sine here, followed by essentially a nothing but a t0. Come on. There we are, and we have then something here which is a sine of r, and we have a cosine of r here. So let's remove this. Let's move this to the right location. I'm even thinking about maybe putting this that no, like this is okay. So this needs to be a cos. So we have all our values here now. So let's just reset the rest, I would say. So we have now here this 0, followed by a 0, followed by a 1, which is part of the identity matrix there. Then it's a 0, 3 zeros, and 1. So yeah, this should actually do our rotation around z. So let's check this. Yeah, and it rotates correctly around that z. So yeah, nice. So we implemented our implemented rotational transform. Nice one. So actually I like this. So now comes something. We will implement the following thing next, that is actually shearing. And let me copy over all of the tests first. They are quite a lot, but don't worry. They are really simple, all of them, but we need all of them because there are a lot of interactions between different values that happen there that we kind of need to take into account. So what we are actually implementing is shearing, and shearing takes a lot of different parameters. And essentially what shearing does is it calculates a transformation which transforms a given pointer vector with regards to all its other points. So you can have essentially it's kind of, if you have something like this and you shear it, you are kind of moving it like this into space, like it's hard to explain. Shearing is, are there any good illustrations anywhere for shearing? Maybe Wikipedia might have something there. No, that's manufacturing. That's not what I want. I want shearing in math. So no shear mapping. Maybe it. Yeah, this could be a good. Is this? Yeah, it's public domain, so I don't need to cut it out later on. You can kind of see what I mean here. It's like perspectively transforming and stretching and moving something with regards to a different plane or a different orientation. Essentially that is what we are implementing there. But essentially it is quite easy what shearing does. Shearing does, if you break it down, you take a shearing parameter list, like how much should each specific coordinate influence another one, and you are just more or less implementing that. So we have those tests here, and we have a test, for example, that x moves in proportion to y, and this is essentially the first parameter we are specifying here. How much of y should influence the moving of x. So if we are in this case specifying that we want to apply one y to x, it will do exactly that. So it will transform this point by applying the proportional value 1 times of y, which is 3, or better said here, 3, to this 2 of x. And essentially we can do this then with another parameter here, by how much should x move in z, in proportion to z. So same thing, we are taking this one, we are taking 1 times z and applying it to there, and we are ending up with 6. And then the next parameter would be how much should y move in proportion to x. So we are doing that, and we are applying this again here. Y should be transformed by 1 times x, which is 2 here, so 3 becomes 5. And so on. Then we have y in proportion to z, and we have z in proportion to x, and we have z in proportion to y. And if we combine all of this stuff up, we can create this kind of movement and transformation there. And yeah, we are actually creating now a shearing matrix which does this. We need this for a lot of different manipulations later on, and I will explain them when we come to that. But it is mostly the most complex transformation we will use. So yeah, I guess we will just do this here again and implement this and call it shearing. So shearing would be then, yeah, the shearing matrix is something I can never remember as well. So let's start by making this identity matrix again, T0 0 0. This is a T0. This is a T1 then. And there we have a 0, and now we have 0, 0, and we need 1, and now we have our identity matrix ready. And now we can, we need a bunch of different other parameters here now, because now we need, yeah, we need essentially which value influences which other value. So we are essentially doing something like, we have an how do they call them here? They have x, y. So how much does y influence x? So followed by let me just print them out here, and then I will add the value, the type there, followed by xz. Then we have yx, then we should have yz, then we should have zx, and then we should have zy. And essentially these are simply the different variants I've showed you before here, like even the the second to last one is how much is the transformation moving z in proportion to x. So it is z to x, so zx. So we are calling it this way, and we are now giving it types here. And now we need to simply put those values again at a specific position. X, Y goes here. Then it is followed by X, Z here. And now I'm really happy I Googled how to disable this formatting, because otherwise this would have simply been not readable. Then we have YX here, YX here. And we have a 1 followed by a 1, and then we have YZ here. And we have ZX down below here. This will be ZX, followed by ZY. So this should create our shearing calculation. So let's just check this. Cargo test shearing, I guess. Yeah, and every one of the calculations is okay. So this seems to work out quite nicely as it should. So let's commit this. Git add source matrix git ci implemented shearing transform. There we go. So yeah, we have now implemented all of those different transformation matrices, and there isn't that much to do now. We don't need to implement any more transformation matrices now for this chapter, but we are testing something different, which wouldn't need essentially a test, but I like the idea of using tests to explain concepts, as the book always does, and essentially it uses those tests here to make sure that something is working out and that we have understood something I want to explain to you as well. So it is essentially explaining what I told you before, that we want all of these different transformations to be possible in one step, because if we have this and if we do this, we can kind of multiply them all together and create essentially a final transformation which does all of them in one go. And first of all, we are ensuring that we can have a sequence of transformations applied to a certain point and transform it and transform it and transform it, and there is actually a result if we do all of those separately. And yeah, I guess this is something Rust doesn't like it doesn't like capital letter variables. So maybe just we could call this, I guess we could just call this A, B, and C then, and then multiply with A, B, and no, not V, C, no, not X, C. Damn it. So yeah, and the same down here, A, B, C. We will take a look at an explanation for that any minute. So let's first take a look at this. What we're actually doing here, we are defining a point, 1, 0, 1 essentially. Then we are defining a rotation matrix and actually rotating this thing by a quarter. Around the x-axis here, as you can see with the x. Then we are scaling it up by uniquely and like the same with a factor of 5 in all of the x's. And then we are moving it by 10, 5, and 7 in the regarding axes. So, and we are doing this we want to do this in this order. We want first, we have this whatever it is thingy in the middle of the world, the coordinate system. It is just there. We are rotating it. Then we are making it bigger, and then we are moving it. So yeah, and we want to do this. So we apply first our rotation by multiplying our rotation matrix with the point. And we are assuming that now the rotation is completed. Then we multiply the result of the first operation, multiply the scaling matrix with the result of the first operation, which should give us our scaled point. And then we multiply the third operation matrix, the third transform matrix, with the result from our second operation here, and we should actually get our final result. And now is something which is quite interesting. If we define those matrices exactly the same and we multiply them up in reverse order, this is essentially because of the operation to come next is always on the left side of the multiplication. You can see this here by the matrix. We didn't multiply the point with the matrix, but the matrix with the point. And we are essentially doing it exactly the same way here. So we need to keep this in mind to always multiply transformation matrices in reverse order. Maybe we will create a nice API for this later on. I will have to see, so that we could just say like, create me a matrix that rotates, transforms, scales and stuff like that, and it will multiply you correctly in the background the right matrix together. But for now, let's take a look at this. So we are doing this in reverse order. So we are starting with this A. We have matrix A, which is our rotation. We have matrix B, which is our scaling. And we have matrix C, which is our translation. And we are multiplying all of them together and get as a result a new matrix. And we only need this final matrix now to be multiplied with the point to get the same result as from all of the different operations here before. And this is actually a really nice thing, because now you can imagine if we would have had 20 of these matrices or 100 or whatever, we could have multiplied them all up, stored the result, and then applied this exact same transformation to like 20,000 points easily. And essentially we need to do this later on, as we need to do all of this kind of operations for a whole bunch of rays, which we are going to cast and fire into our scene and see where they bounce off and what they do. So we actually need this, and we need this to be reasonably fast. We are not going to win any speed competitions here with our code, because it is not optimized at all. And essentially, I don't really know what I'm doing here in Rust, because I have no idea how Rust actually works, or what is fast there or what is not. And I'm not even trying to make it fast. Like I'm not even trying to apply the knowledge I have from other algorithms and systems to make it faster than it might be in the state we are currently doing it, because I want to make it as understandably as possible and to be as close to the book as possible, just to follow along this whole process, which is really nice, and I really like it. So yeah. So let's run those last two tests, I guess, and let's check if they work, and they should. So let's run all tests, and they are working. So we have now proven that we can actually chain all these transforms up, create one final transformation matrix, apply this to a point, and we get the same result as if we do it in sequence. So this is really, really nice. So let's commit this, I guess. Implemented test to showcase transformations can be transformation matrices. World transformation matrices can be created. Something like that, I guess. And let's push this. Now we are actually at the end of chapter 4, which is quite nice. and we did it. We did all the stuff that was yeah, kind of very mathematically and times boring and maybe a little bit hard to come by, but now we have done this fundamental work here, and we can go on and do the fun stuff like going along and firing our first race into the scene and ray tracing a sphere, which we'll do in the next chapter. But first, we will actually see and yeah, first we will actually implement putting it all together thing, and it will look the following. We will, according to the book, we should create a simple picture which represents a clock, like a round clock, and there should be a point simply on the canvas for each of our hours. So there should be one here, one here, one here, one here at 3 o'clock, one at 4, 5, 6, 7, and so on and so on. So we just want those points at the numbers, and we want to use all of our different kinds of transformation functions and stuff like that for this. And yeah, so I guess we are going and doing this just right now. So let's create ourselves. Where are we here? Let's create ourselves a chapter 3, I guess. Let's maybe copy and start from chapter 2, even though we are not going to use much of those, but I guess it will be most easy to just start with this. And yeah, let's see what we need from here. We don't need an environment anymore. We don't need a projectile anymore. We don't even need those implementations for ticking along anymore. We don't need from point for canvas. Do we need this? Maybe we do need the screen. Maybe we can reuse this actually. So we have this pixel, which was an enum, which would be either a coordinate or, yeah. And we had from point for canvas. From point for canvas? Oh, so yeah, we could just put a point in and a canvas and we would get back the corresponding thingy inside the canvas clamped to it. So yeah, we actually can use this. So we will keep that. And we don't need this anymore. We, however, need a canvas. We will see how large we need it. Let's make it, I guess, 500 by 500 for now. We need a color here. Yellow is fine, I guess. We don't need this anymore. We don't need the projectile or even the iteration anymore. We don't need all this here. Yeah, this is not, we don't need this. We may need this later on, but we can re-implement it. Let's just check. So let's remove this here and let's leave this code in here, which writes us our output data to the disk, and then let's just start implementing. So I guess the first thing we want to think about is how will this look. So let me quickly kind of try and sketch this up here within the document. So we will have a point here. We will, I guess, maybe here we will. Yeah, this is not so yeah, it will not be very round, I guess. Maybe like this, but no. Yeah, you can't actually create a round circle within an ASCII document. It's really hard. You may be able to do this with some sort of Unicode characters, but not so easy. So what we are going to do is first, I guess, and just now
thinking out loud and trying. It might not work what I'm doing here. So we want to calculate all of these different points. The first thing we would like to do is, I guess, move our entire coordinate space maybe, so that our origin is in the middle of our screen. So let's actually try this. Let's define, I guess, a new origin maybe. New origin, which would be then a point, I guess. And this point will be, we'll entirely think this through in 2 dimensions, more or less. We won't use one of those dimensions because why should we? So let's just do this in XY then, I guess. Yeah, so let's create a new origin there, which would be yeah, where would it be? Essentially, our canvas origin is in the top left, but our point origin is in the bottom left. I guess we are already converting here in our from point for canvas thingy, aren't we? Yes, we are already converting this, so we don't need to think about that. Our origin from our view and perspective is in the bottom left. So let's so there we are. New origin is a tuple and it's a point, and it's then, I guess, moved up by half and in both directions. So it would be, let's maybe define this. Can we do a const here? I would like that. I have no idea if this works in Rust, but it doesn't complain about the keyword yet. So let's see. Let's do a width here, which might be 500 then, and maybe a const height, which is 500 here. So we can easily. This does seem to work, at least. I like that. So if I'm now going to do it with here, it won't work, I guess. It does work? That's kind of interesting. I guess my IDE did just, or again, not see that it should take this file up or something like that, because I have the slight fear that this is not yet tracked and compiled. Let me just quickly restart this one here, because, okay, yeah, there we go. So missing type. Okay, so this one needs a type. What is canvas? Actually takes a U size. So yeah, why not? Let's do a U size here. And let's make this a U size as well. We can easily do this. And this works for the canvas, but of course it might not work for this one, but we will see. So this point here now needs 0. Come on. Needs a 0.0 here. And then it might complain about the typing. Yes, U size is not a float. Yeah, of course it is not. But can we compile it or convert it, better said, into a float? No, we cannot. So, but we might be able to just do something like this. Yeah. So now we have more or less enforced it to use the F64 implementation. Type annotations needed for ray tracer canvas T cannot infer. Okay, why can it not infer the type here? Let's constant width should have an uppercase name. Oh, okay. So then let's do this. I guess because constants should have this naming then. So yeah, we can adhere to this. Width and height. Variable does not need to be mutable. Yeah, not yet. Okay, so let's not let's not get into this yet, because later on it needs to be mutable for us in order to set pixels on it. So let's go ahead now. We have a new origin now, which is essentially in the oh no. I'm assuming it is divisible by 2, I guess. Yeah, so I guess I want to do it this way. Yeah, and then let's create let origin transform equal matrix translate translate? Did we name it translate or translation? And did we even import? We did not import matrix here. So let's actually import that. And then let's check if this is matrix. Why does it not? Did we import the right matrix thingy here? Ray tracer challenge matrix. Yes, it is the right one. So translation was it, I guess? Yeah, translation. So give me a translation of new origin.x followed by new origin.y followed by new origin.z. Maybe we should create a translation function which takes a point. Yeah, but let's not worry about this now. Just to ease things a little bit, because I guess we will later on a lot of times just translate by a specific point. But let's see. So now we have this origin transform, which is kind of nice. This should actually move everything into the middle of our screen. So what I'm thinking now is, do we need to move into the middle of the screen, or do we need to move actually do we need to do the inverse of that? So if we are going to draw a point at, let's say 1, 1, it should actually end up the middle plus 1, 1. So yeah, this is actually right. We are moving our rendering origin. If we apply this to a calculation, would be in the middle of the screen. That's really nice. That makes things a lot easier. So now we can think about, I guess, rotation. So if we now rotate things, just we want to actually print 12 numbers, I guess. So let's do for hour in 0 to 12. Do the following, like do how do we now get this point? Essentially we could now move up y a certain amount, like the radius we want to use for drawing, I guess. So maybe do this like const r is, let's do maybe 200. Seems to be reasonable. If we have 500 by 500, 250 is the half. Let's try this, I guess. So const r is 200, and then we could easily move this direction into y, but we need to do it for all of those clock thingies, so we need to rotate everything. So we first the point needs to be, or the origin needs to be we need to rotate this by the amount we want there. So 12 o'clock and so on, we need to rotate this along. So let's just create let's call it rotation transform, I guess, which will be a matrix rotation. And now we are rotating around the z-axis, but I'm not 100% sure in which direction we are. I guess the z-axis comes at us, so... Or goes it into? Does it go into the screen? The z-axis comes at us. So we are rotating around clockwise, yes. So if we are rotating z by, and now this should be quite easy to calculate actually, if we would have the pi implementation here. So use... Why do we have, oh yes, use std f64 const pi, there it is. So now we have this pi here, and we actually need 2 times pi, and we need to divide this by 12. And I guess multiply it again with the hour we want to create. So this should be our rotation, each 12th of a full rotation. Yeah, I guess so. I guess this should. And then of course we need. Oh, can we do something like into here? Most likely not. So can we do something like as f64, because this is essentially what I would like to do there. Attempt to use non-constant value in a constant non-constant value. What? Attempt to use a non-constant value in a constant non-constant value. What kind of error message is that even? A missing type for const. Const? Oh, this shouldn't have been const here. Cannot multiply integer by f64. So this is actually, yeah, it is obviously a floating point all along, but yeah. And we need to cast this as well into a floating point to do this calculation. So this should actually rotate then our point. And if we now go along and just take this, let's just call it let point be tuple point, and we do this like we take the what is it now? We are on the x. The x isn't moving. We are just going 0.0 on the x. The y is essentially our radius. The z has nothing there. So we are just moving up y by this. We could do this by a translation matrix, by the way, as well, and just plot the point 0, 0, but why should we? So, yeah, I guess we now have this point. And if we now go ahead and first of all have this this origin. No, wait, let me think. We need to do it in reverse order. So first of all, we need the rotation transform applied to this one. So rotation transform multiplied by origin transform multiplied by the point should actually give us transformed point. So this should actually give us something we can now draw on the canvas. So now our from point for canvas function comes into place. So from point for canvas, which takes a transformed point, I guess, and a canvas. and we are matching this against yeah, we are matching this against either a coordinate which has an x and a y, which we want now, or it has something else, and something else means panic could not map point to screen/canvas. So we have this here and we have this there, and if we have a coordinate, we are telling the canvas to, wasn't it set pixel? Right pixel. We are doing right pixel at x, y, with the color we have defined before, I guess. And there is a comma and there is a cannot find struct variant or union type coordinate. Oh, I guess we need to call this by its full name. Yeah. So we have panic here, and there needs to be a parenthesis around that, and now we can format that, and then we see cannot find function from point for canvas in this scope. From point for, but it is, oh, it's inside of pixel, so we need to do pixel from point for canvas. And mismatch types, expected reference, found struct canvas, note, expected reference, it expects a reference to a canvas, so let's give it a reference to a canvas. And now it's not complaining anymore, and I guess we can try and compile this. So let's do this. Cargo run -- bin chapter 03. Unwrap on a none value in wherever. Chapter 323. What is 23? So I guess we did something wrong there, maybe. So we are actually getting the round value here, and we are converting it here to a U size, and this fails. So this value seems to be, I don't know where it actually lies, but it does not lie within something we want to have there. So maybe we could just go ahead and print line this what was it? I think it was like this transformed point here, so that we can see actually what it is crashing at. So what point it tries to put somewhere. And so the first point it tries to do is x to 50, which is the middle, and y 450, which is the middle plus 200. This is our 12 o'clock position. That seems okay. So the next thing then is x minus 8. Okay, there is something quite wrong. And I guess this is why it cannot be mapped to the yeah, because we are converting it to a U size and it is rounding it to a negative value. And then, so what we actually would need to do is, and this is quite okay, I guess, is we would need to do it. One part of this check would need to be here. Like if it's negative, it should be out of out of bounds of the canvas here quicker, before even trying to do this weird casting, because it then cannot do it essentially. So let's try it like this. It won't fix our problem, but it should maybe give us a more meaningful error message. So panic could not map point to screen canvas. Yeah, so maybe we should include in our out of bounds thingy here. Maybe we should include an x, which is what is it then? Yeah, like like a T, I guess, and a Y, which is a T, I guess, and this is a T then, I guess. And this is then the implementation of this template type. And now I could return out of bounds. Wait a second, how do I do it here? I just simply do it directly. I could, X is now RX, Y is now RY. Yes. And I could do the same thing here, I guess. So cannot find type T in this. Yeah, we need it actually here then. And I guess we don't need that here then again. And it gives you a pixel of type T. And now this has this where field. And yeah, I guess this should... Field is never read. Yeah. It's never read because we are not currently doing this. Not, how is it called? Out of bounds. So let's actually read this. Out of bounds. And it's giving us an X and a Y. And I guess we can met node point to screen out of bounds, and then we are just, I guess, putting yeah, maybe just doing this and doing it like this so that the coordinate is displayed there. I guess that would be kind of okay. So, and we need a pixel here to qualify it. Not a pixel, but a pixel or pixel. No, it's a pixel. And yeah. So now let's try this again, and we should have yeah. So out of bounds, -8 to 515 is definitely out of bounds. I get that. So, and maybe I want spacing around this, I guess, to ease the reading. Yeah, it's better readable this way. So, okay, now we have at least proper error messages when we run into this problem again. So, let's now see what we did wrong here. Maybe we did the transformation in the wrong order. That could be possible. So let's just try if this would fix things and then think about why it fixes things. Rotation transform multiplied by point. And let's take a look at this. So yeah, and I guess this fixes things. Let's take a look at what it now wrote. And it is our clock. I'm not sure you can see this. Let me make it a little bit bigger so that you can see all the different pixels. It is our clock. We have drawn our clock image. So that's quite nice. And we have our PNG here, which is quite the size difference. 2 kilobytes for the PNG and 1.5 whooping megabytes for the PPM. But yeah, it's the PNG is compressed and stuff like that. So yeah, but this works. But now let me take a look at why it works and why this is the right way of transforming things. So maybe we should apply this in order then by themselves to just see. So we have P1 equals we want the origin transform multiplied by the point, and then we want the P2 is then the rotation transform multiplied by P1, and then we have the transformed point equals P2. So let's comment this out just to check if this actually yields the same result, or if I'm just okay. I seem to be thinking wrong here. So why is actually the transformation of our target point. Why do we obviously need to first rotate and then do the origin movement. So why is this? So let's think about this. We want our point to be at a specific location. So if we do not rotate it, let's say we rotate it by 45 degrees. So we would have the point there, like a clock hand like this, and we want to rotate it like this. Oh yeah, of course. If we are doing the origin move before the rotation, then we are always rotating around the z-axis. So the z-axis in our coordinate system base. So in our 0 position, which is down there, down the bottom left. So if we are rotating it's definitely the first order. We need to rotate around this. There, we need to rotate around that. Like here is our thingy, and we are rotating it like this, and then we are moving it up into the middle. Yeah, it makes perfect sense if you think about this, but this is kind of hard sometimes, and this is why this example here is great, just to see that this can work, or better said, may not work if you do it in the wrong way. So if we do it this way, it works, and I actually like it. But now I want to remove those. Maybe we could, yeah, but why not? We could just print before that writing pixel and just this position there. I actually kind of like this output so that we see what is actually happening there. It is writing all those coordinate tuples and or let's just say writing or rendering point is maybe the, or just point would be the more appropriate description. Yeah, and this is working as it should now, after some back and forth and thinking about matrices. And as you can see, it's not that hard to do this or to work with that once you've thought about it a little bit, but you need some more working with it, as did I now, or am I going to do or to need, because I haven't done all this 3D rendering stuff in quite a while. I've implemented something like a 3D renderer, but not a ray tracer, a while back for work, but that's quite some time ago. And you need to put your mind into a state where you can actually think about those things more easily. It happens automatically quite fast. So yeah, I guess now we have completed chapter. It's not even chapter 3. We need to rename this because we did not implement something for chapter 3, because chapter 3 was only basic matrix implementations. So yeah, let's commit this. Git add source bin chapter 4 git ci -m implemented chapter 4 challenge, and push this. So yeah, we are at the end of this chapter, and as I've said, the next one will actually be the implementation of our first bouncing race or throwing race, shooting race, however you might want to call it, into the scene and intersecting it with a sphere, which is mathematically quite interesting, and we will see how we can do this and realize this. And yeah, I see you there. And by the way, I guess I liked the way we did this here now with the copying over the tests, then just talking about them and then implementing the code. I think this worked a lot better than me writing the tests within the sessions, and I guess I will do this again. And furthermore, I liked my cutout appearance in the bottom right. I will need to of course see this video to to get a better idea of if it worked quite well later on when I'm editing it a little bit, or at least skipping over it and making sure it is fine. Yeah, but I guess it worked reasonably fine, and I guess yeah, this is quite nice and works out. So maybe we'll keep this. Maybe I will even need to get a real green screen behind me. Let's see. I've no idea yet. But I liked actually how this worked out. So yeah, we will see. Thanks again for watching. Thanks again for following me during these sessions, and I see you for the next chapter. Thank you and bye.